Thermochemistry. Thermochemistry has to do with energy, which is the ability to do work and produce heat. Heat, we know, is the flow of energy, and usually goes from things that are hot to things that are cold. Temperature is a measure of average kinetic energy of particles, and we usually refer to high temperatures where the kinetic energy is really high, and low temperatures are when the kinetic energy of particles are really low. Exothermic reactions or processes are when energy is released. Endothermic reactions or processes is when energy is absorbed. As you can see in these pictures, energy is starting from the system, which is this, and going outwards, whereas an endothermic reaction or process is the reverse. Here we have a potential energy diagram of a reaction. We start off with the reactants, and we end with the products. In order to get from reactants to products, we have to apply what we call the activation energy, which is the minimum amount of energy needed to get a reaction started. The difference between the reactants and products is what we call the enthalpy change or change in heat. In this case, we have lost energy or lost heat because the reactants have higher energy than the products do. In this case, we have a negative delta H, which means it's exothermic. If we have a positive delta H, this would mean it would be endothermic. A catalyst, we know, is something that speeds up a chemical reaction by lowering the activation energy. So in black, we have the same reaction, but just with a catalyst added. And therefore, it gets from the reactants to the products a lot faster. It still gets from the reactants and products the same starting and ending point, but it gets there in a different pathway. And the way it does that is by lowering the activation energy. We can calculate energy by using M times C times delta T. Energy, we use units called calories or joules. If we get a positive E, that means it's endothermic. If we get a negative E, that means it's exothermic. Here are some conversion factors. 1 little cal equals 4.184 joules. 1,000 calories equals 1 big calorie or food calorie, or what we call 1 kcalorie. And 1 food calorie also equals 4.184 kilojoules. M stands for mass. Here's another conversion factor where 1 kilogram equals 1,000 grams. Sometimes we refer to water as a volume, and we know that 1 milliliter of water equals 1 gram of water. The specific heat of the substance is the amount of energy needed to raise 1 gram of that substance by 1 degree Celsius. If we're talking about water, water equals 1 calorie per gram degree Celsius, or 4.184 joules per gram degree Celsius. Delta T refers to the change in temperature, where we have a starting temperature and a final temperature, and we subtract those two numbers. Calorimetry, we're going to use the idea that the amount of energy in the universe is equal to each other or constant. So if you have two systems in place, one system is going to absorb energy, the other system is going to release energy. And we use M times T times delta T and negative M times C times delta T for the one that's releasing energy. This is a phase change chart where we are changing water from a solid to a liquid to a gas. The solid energy equals mass times 0.5, which is the specific heat of solid ice, times the change in temperature. And the change in temperature is only from this point to 0. On the flat piece, we call that fusion. And it is basically the phase change from a solid to a liquid. And it takes 80 calories per gram to change 1 gram of water from a solid phase to the liquid phase. In the liquid phase, energy equals mass times 1, which is the specific heat of water, times change in temperature. And remember, the change in temperature goes from 0 to 100 in the liquid phase. Once it's at 100, it starts vaporizing or changing state from a liquid to a solid or to a gas. And it takes 500 calories per gram to do that. Once that gas has reached 100 degrees, it now is in the gas phase. In order to calculate the amount of energy that gas has, we're going to calculate it by mass times 0.4, which is the specific heat of gas, times delta T. Delta T starts at 100, but then it goes to some value above 100. Thermostoic has to do with trying to figure out how much energy is needed in chemical reactions given grams. We need to be able to recognize exo versus endothermic reactions. If we have an exothermic reaction, we know that energy is a product, or we have a negative delta H. In endothermic reactions, we have energy as a reactant and a positive delta H. When we solve problems, we convert grams to moles, and then moles to kilojoules. And the way we do that, this piece, is by looking at the balanced equation and using coefficients. Hess's law has to do with the sum of all delta H's from all the intermediary reactions, and the sum of all those equal the total delta H for the entire reaction. In order to figure out the total delta H, sometimes you multiply reactions. When you multiply a reaction, you have to multiply by an integer to get the final delta H. And then sometimes you have to flip reactions, and when you flip them, you have to reverse the delta H. When you do that, you can add all the terms together, and then you'll get the final delta H. Gibbs free energy has to do with thermodynamics, which determines whether or not a reaction is spontaneous. We use the equation delta G equals delta H minus T times delta S. Negative G equals spontaneous reaction. A plus G equals a non-spontaneous reaction. A negative H equals exothermic. A positive H equals endothermic. A negative S equals disordered. A positive S equals ordered. When we're talking about a favorable condition, which means a negative delta G, we have a negative H and a positive S. Unfavorable conditions are a positive H and a negative S. And temperature-dependent conditions, when we have both negative H and S, or both positive H and S. If we have both negative H and S, favorable conditions would be a low temperature. If we have both positive H and S, that means we need to have a high temperature. Nuclear chemistry has to do with decay. And decay is when an unstable particles become stable by removing particles and energy. There's different types of decay out there. There's alpha decay, which produces an alpha particle, which is basically a helium nucleus. Beta decay produces basically an electron. A gamma particle is basically energy. Electron capture is when you are capturing an electron. And positron production is when you're basically capturing a proton. Fission has to do with the breaking apart of nuclei by other particles and releasing energy. This is how nuclear reactors work, where you take nuclei and you break them apart. In doing so, you release tons of energy that we can use. Fission is the combining of nuclei. And